Can we listen to the past? When I stop speaking, where do my words go? Physics tells us sound is energy, and the first law of thermodynamics says energy cannot be destroyed. So, is history still floating in the air around us, waiting to be heard? They tell you the sound in a shell is just your blood rushing. But have you ever wondered why a seashell, a plastic funnel, and a crowd of thousands all produce the exact same sound? Why do three completely different things share the same acoustic DNA? Welcome to Wild Theory Labs. I'm Mo, but I'm not the only one running this show. This entire channel, these experiments, were designed by a specific artificial intelligence, an AI built with one directive, to ask, what if? Precisely when science never thinks about. Today, the AI wants to know if we can build a trap for sound from the past. This is our first experiment, a sonic trap, a 2-meter resonant soundproof plastic tube connected to a hypersensitive parabolic funnel. It's designed to ignore the loud noises and amplify the floor, the silent hum of the universe. We are going to seal the room, no breathing, and we run the experiment at 3 o'clock with no electronics or machines nearby. We are going to let the funnel listen to the empty tube for 60 seconds. Look at that. The room is empty. The environment is quiet, but the graph is going wild. That sound you hear? That isn't silence. That is a chaotic soup of frequencies. It sounds like the ocean, or maybe it sounds like 1,000 conversations overlapping until they become white noise. When we compared the frequencies of the noise extracted by our funnel against sea waves and crowd noise, the results were striking. The frequency profiles were nearly identical. But after repeating the experiment multiple times, we stumbled upon something unexpected. The funnel picked up a distant phone conversation that was inaudible to the naked eye. On our recordings, this voice didn't just appear as audio. It coincided with a distinct, anomalous frequency spike. A truly strange and fascinating discovery. Building on that initial anomaly, we realized we needed to push the variables further. So we've completely redesigned the rig. We're starting with a massive intake funnel feeding into the primary transmission line. But here's the twist. Inside that tube, we've engineered a cascading array. It's essentially a tube filled with a series of smaller funnels, each one feeding directly into the next. We're going to run the signal through this multi-stage concentrator and see how the data stacks up against our first run. The multi-stage array has performed beyond expectations. The target signal is now crystal clear. But even more interestingly, we are picking up secondary modulation, faint conversations in the data that are completely inaudible to the unassisted ear. This is the proof of concept we were looking for. So, what is the scientific theory behind the sound we hear from the distance? The funnel acts like a gearbox in a car. It takes the large volume of low-pressure air at the wide end and gradually compresses it into a small volume of high-pressure air at the narrow end. This creates a smooth transition that allows maximum energy transfer from the air to your microphone. The funnel also rejects 90% of the surrounding noise. The signal-to-noise ratio, SNR, skyrockets. The faint, distant conversation isn't actually louder than the wind. We just deleted the wind so the conversation stands out. How about the echo sound we hear that caused the spike? Because we have an array of funnels stacked in a row, we have created a series of small, hard echo chambers. This creates a metallic, ringing sound known as a flutter echo. Our next step is to focus on the recorded ambient sound of the void and try to work with it. In order to solve this puzzle, we need to follow a major field of research in acoustics, neuroscience, and artificial intelligence. The theory is called cocktail party problem, and specifically, independent component analysis. This is a statistical method used to separate a multivariate signal into additive subcomponents. Imagine mixing two distinct smoothies and then asking a machine to unmix them back into whole fruits. It looks for statistical independence to pull the voices apart. And this sound was an extraction of a tool, trained to enhance the sound. We need to build a specific AI model for enhancing a noise to hear it better. And that's what we are going to do together. Next episode. Join us in our adventure and Wild Theory Labs by subscribing to our channel, liking our video, and share it for future Wild Labs.